Okay, good day everyone. Okay, so this will be the part 3 of our series for the lecture Shear and Moment Diagrams. Okay, so if you can remember, this is our last example, okay, in the second video of this series, our lecture series. Okay, so today we will solve uh, solve your shear and moment diagrams by another method. Okay? This time, we do shear and moment equations. Okay? So, unlike the first method that I have taught you, this method is flexible, in which you can actually compute the shear at any given length, or at any given point inside the beam. Okay, whether it is located not at the point of reaction. Okay, so last time we did it differently. Okay, without further ado, I will introduce to you how to construct the shear and moment equations. Okay, there are actually uh, several ways in order to uh, to to construct your shear and moment equations. Okay, so but this time we will discuss in an easier way. Okay, so particularly um, this example. Okay, so if you remember our first example in the second video, we will repeat to construct the shear and moment diagram, this time by shear and moment equations. Okay, so this is your beam, and this is the computed reaction. So okay, I will not recompute anymore the reactions at the supports of this simple span beam, because we have discussed it in the second video. Okay, so but this time we will have a shear and moment equations. Okay, so in order to do that, we will divide our beam into uh, various sections. Okay, so let us say, because this is reactions at the support. Okay, so this is actually a pinned support here on the second video, and this is a ruler support actually. Okay, so in between this support and this load, this point load, we take it as section 1. Okay, between this 80 kilonewton load force and this distributed load, we name it as section 3. And along, okay, along this distributed load, we can say it is section 3. Okay, so why do we do sectioning uh, in this in doing the in constructing the shear and moment equation? Okay, so it is because at these different points, your loading manner changes. So because your loading changes, your shear and moment also changes in its behavior at these spaces. So that's why we do sections. Okay, we divide into section. Okay, so let us say section 1. Okay, so section 1, so the x here. Okay, so in which the x section here is x is equal to 0. Okay, x is equal to 0 to x is equal to 2. Okay, so looking upon the graph. Okay, so in our first video, I have discussed the concepts of this. Okay, so we have an 85 kilonewton upward force from the supports. Okay, so since from x equals 0 to x equals 2, the only force that is acting is this 85 kilonewton force. So therefore, your shear is equivalent to that force. So your V here, okay? So your V here is, okay? So let's have a drawing, okay? So this is your support, okay? You have the 85 kilonewton force. This is 2 meters. And this is AX. Okay, at section 1, there is no, okay, there is no other vertical load rather than this AY. So therefore, your V is equal to AY. Okay, so therefore, your shear equation at this point is V is equal to 85 kilonewton or 85. Okay, so that is your force. And then, what about your moment? So your moment, okay, so your moment is equivalent to, okay, if you remember our first video, okay, so if this is your shear, a constant, you integrate that one, that is, it will be 85x. So this is your moment equation at section 1. Okay, so how do you draw that in your shear and moment diagram? Okay, so let us try to draw it. Okay, so let us say this is your Vx diagram. Okay, so this is the line that represents the 0. Okay, that's the 0 shear. And let us say for the moment diagram, okay, let's put it there. Okay, so I'm sorry if I could not have a perfect straight line. Okay, so just assume this is a straight line, mx. So this is your shear diagram and moment diagram. So at this point, you have 85. And then, okay, it stays that way until this point. It is also 85 kilonewton at this point. Okay? And then we have 85x. Okay? So we know that equation, okay, visiting your knowledge in algebra, 85x, okay, so this is your variable, okay, in your algebra, this is actually y, okay, this is similar to y, but here it is moment, so this is actually an increasing graph, okay, 85x, meaning when x equals 0, it is 0, but when x is equal to 1, it became 75, somewhere here. And when it became, the x is 2, it became 170. So it is increasing. Okay? So it is like this. 85 kilonewton times 2. So this is 85 times 2. We have 170 kilonewton meter. Okay? It is increasing. And then we have section 2, in which in between this 80 kilonewton force and this shear, this distributed load. Okay, so okay, section 2. Okay, so we have positive, okay, it's positive. Okay, if you review our in the first part of our video, okay, first part of our video series, I explained in that part what is the shear and moment, the portion of shear and moment equations at a certain load or support reactions. Because this is upward, so it's positive. But if it's downward, then it will be negative. Okay? So section 2 here is from x is equal to 2 to x equals to 4. Okay? So you might be asking, at x equals 2, sir, there is 80 kilonewton 80 kilonewton downward load. Okay? So we did not include this one because at the left, okay, at the left side, 2 meters, there is no load yet, but after that 2 meters, the 80 kilonewton exists. So therefore, your, let us say, we are finished with section 2. Okay, so we have 80 kilonewton here. And then we have 2 meter here, 2 meter. Okay. Let's have 85 kilonewton. Okay. So as you can see, okay, your force here is 85. Okay, there is an existing load 85 upward, and there is a downward force. So therefore, your B is equivalent to the sum of these forces. So you have 85, because it's upward, so it's positive, and then downward 80, so it's negative 80. So your B here is 5. So since it is a constant, it will become 5 kilonewton. Okay, so that is your shear equation at this point. Okay, so from this at section 2. So that's okay, so that's it. Okay, so that is your shear. But somehow your M, okay, so what will you gonna do? Okay, so here we have, okay, so one thing you should do is, okay, visit your table. Okay, visit your the table you found in our first video. Okay, so we have 85 kilonewton acting at the support. So you have 85x. Okay? And then again, after 2 meters, you have 80 kilonewton downward acting 2 meters from the support. Okay? So we have an x here. Okay? So let us say your x is any random distance from your leftmost support. So here, your m is equal to 85, because there is an upward force, 85 kilonewton at the leftmost support. So we have 85x. Okay, and then because there is an 80 kilonewton acting 2 meters from the support, so we have minus 80 times x minus 2. Okay, so if you remember on our first video, okay, part 1. Okay, so to those who have not seen the first video yet, see shear and moment equations part 1. Okay, so this is your moment equation from x equals to 2 to x equals to 4. Okay, so how do it translate in your moment shear and moment diagram? Okay, so this is your shear and moment diagram. Okay, so your shear equation from 2 to 4 is 5 meters. Okay, so therefore there is a point where it will go down. So this is 5 kilonewton. So I apologize if it's not straight. It's supposed to be horizontally straight. Okay, until this area. This is also 5 kilonewton. Okay, so how do you translate this equation? Okay, so actually you can simplify this equation actually. So if you want, you can simplify this equation so that you will get a simpler one. So you have, let us say, m is equal to 85x minus 80x plus 160. So we have 5x equals minus plus 160. Okay, so you can take this as your m equation. Okay, simplified. Okay, but somehow this is actually acceptable. Okay, so if I will be your instructor and you solve, you say that this is the shear equation of this section 2, so it's okay already. But somehow you can simplify it so that you can easily track the value of your shear diagram at any point. So this is your um, your moment simplified moment formula from of section 2, which is from x equals to 2 to x equals to 4. Okay, so let us check. If x is equal to 2, okay, 5 times 2 plus 160 will be 170. Okay, so this is 170. But if your x is equal to 4, which is the end point, 5 times 4 is 20 plus 60. This will be 180. So this will be 180 kilonewton. Okay? So since this is an x, okay? X variable, so it is actually increasing straight. Okay? Okay, so we have section 3, the last section. Okay, so we have section 3. So here, we already knew, okay, let's draw again. We have 85 kilonewton AY, AX equals to 0, and from 2 meters, it has an 80 kilonewton load downward, and after another, okay, there is a load, which is 4 meters, 25 kilonewton downward, kilonewton meter, okay? So if that is the case, okay, so we write again your shear. Your shear is 85, okay, 85 kilonewton. Then there is a point load somewhere in 2 meters, so minus 80 because it's downward. And then there is there is a force which is 25 kilonewton. So how do you draw its shear equation? So its shear equation, okay, as you can see in our first video, as I have discussed, it will become negative 25 times x minus the distance, okay, minus a. The a here is 2 meters plus 2 meters, okay? So this is 4. So your V is 5, okay? Okay, so it's 5 minus, okay, so let's simplify, negative 25x plus 100. So your V here is 100 plus 5 is 105. So 25x plus 100. So this is your shear equation. So let's start. Okay. Section 3 is, okay, section 3 is x is equal to, okay, section 3 here is x is equal to 4 meters, 2x is equal to 8 meters, okay? So let's divide this one by this, okay? So we have a limited space. So when x is equal to 4, okay, your shear, this is 105 because, okay, sorry, I pardon, because this should be 105, okay, 5 plus 100. Okay, when your x is equal to 4, since your section 3 is from x equals to 4 to x equals to 8, so your V is 5, okay? 4 times 25, negative 25 is negative 100, plus 105 is 5. So it stays there, 5. But somehow, if your x is equal to 8, which is the end of this distributed load, okay? So 8 times negative 25 is how much? 8 times negative 25 is negative 200, plus 105 is negative 95. And because it has it has a linear graph, okay, because it is negative 25x, So it will be linearly downward. Which is negative 95 kilonewton. And since the last part will be this by, since there is a by, there is a support reaction which is vertical 95 kilonewton, so therefore negative 95 plus 95, so your shear your end shear will be 0 kilonewton at this point because there is a vertical 95 kilonewton. Okay, so you have two shear acting on these supports. We have negative 95 and 0. So this is your shear equation. What about your moment equation? Okay, so since we have no okay, we have no space here. Okay, so we may use another okay, so we use another board. Okay, so we have section 3. Okay, we know that section 3 is from x to 4 to x to 8. Okay, so we already know that your v is equivalent to negative 25x plus 105. So your moment here, okay, so maybe I will draw again the drawing so that we will not be, okay, so we have 85 kilonewton ay, ax is here 0, okay, 2 meters, 80 kilonewton, another 2 meters, and then the distributed load 25 kilonewton meter. Okay, so we have moment, we have 85 kilonewton acting on the leftmost support. So it will, your moment equation is 85x, and then we have downward force, vertical point load 80 kilonewton acting 2 meters away from your leftmost support. So we have negative 80x minus the distance of that formula, okay, of that point load from your left support. So that is x minus 2. And then we have a distributed load, negative 25 kilonewton. So how it will translate into moment equations. So since it is 2 plus 2, 4 meters away from your left support, so we have x minus 4 squared, okay, over 2. Okay, so so that will be our moment equation from this point to that point. Okay, so we can simplify actually. 85x minus negative 80x plus 160 minus, okay, this is 12.5 x squared minus 8x plus 16. So we have 85 minus 80. Okay, so we can resimplify this. This is 5x plus 160 minus 12.5 x squared. 12.5 times negative 8 is 100x. Negative 12.5 times 16 is negative 200. So therefore your m, okay, combine this one. So we have negative 12.5 x squared plus 100x minus 200. So this will be, okay, This will be our, no, what this is 105. This will be our moment formula. Okay? This will be our moment equation from at section 3 at x equals to 4 to x is equal to 8. Okay? So we can actually, okay? We can actually, there is another thing. Okay? We can actually locate, oh, we can actually locate your maximum moment equating your v equals to 0. Okay? So here, you can see in section 3, there is somewhere, there is actually a value in which your v here, okay? So you can see on this graph, on our moment diagram, in which um, your shear is 0. Okay? So we can equate that one in order to locate this point from your left support. Okay? So we have, okay, so let's solve here. So we have here V is equal to negative 25x plus 105. And then we equate that to 0. So we can know this value. The value of your x in which your B is equal to 0. Okay? And then we use that one in order to note your maximum moment. So negative 25x plus 100 equals to 0. So we will, okay, so using calculator or using simple algebraic manipulation, so negative 25x is equal to negative 105. Negative 105 divided negative 25 is how much? 4.2 meters. So this is 4.2 meters here. Okay? So please take note, this is not actually included in your shear and moment shear and moment diagram. We just include this in order that we will know the maximum value of M. Okay? So at this point, there lies, okay, at V equals to 0, it actually corresponds to the maximum value of your moment at that section. Also here we have section 3. The maximum moment at section 3 will be at x is equal to 4.2. Okay? So maybe I will find a calculator. Okay? So we have, so by using a calculator, okay? So we try x is equal to 4.2 and then we substitute the value here. So we know the value of your m at x equals 4.2. So we have negative 12.5, 4.2 squared plus 105 times 4.2 minus 200. Okay? Okay, so I'm sorry, negative 200 plus 160, it should be 40, okay? It should be 40, sorry. Should be 40. Oh, no, negative 40. Okay? So, if that is the case, there is a value which is 180.5 kilonewton meter. Okay? This is kilonewton meter. Okay? So, as we all know, because it is a 0 degree, this is a 1 degree curve. Okay? So, horizontal line is 0 degree, 1 degree. So this is actually a 2-degree curve. So that is why we draw it that way. 2 degree. As you can see here, it is a 2-degree curve because it's a maximum power. Oh, in this formula, the maximum coefficient of its power is 2. So that is a 2-second-degree curve. And this one, okay, so we have negative 25x. It has x to the power of 1, so it is 1-degree curve. So therefore, it should be a 2-degree curve. So this is your shear and moment diagram. Okay? So you may not include this one in your shear and moment diagram. So for the sake of solving, since we have no space, so I included it here. Okay? So this is this will be your actual shear and moment diagram. Do not include this one. Okay? Okay? So here you can see negative 180.5 kilonewton, then it will end up at 0 kilonewton meter. Okay? 0 and 0. In order to check if your moment is correct, okay? So as you can see, just a few minutes before, I have an erroneous solution in this area. You can actually check if your moment equation or shear equation is right if in the end uh, it will become 0. But if it will not become 0, your solution is erroneous. So here, this formula should have 0 value at x equals to 8, since the length of your beam is equal to 8. So let's try negative 12.5 times 8 squared plus 105 times 8 minus 40. Okay? So since it equates to 0, so our shear and moment equations is equal to 0. Okay? So that is a method we use, okay, in solving shear and moment equations using in constructing shear and moment for diagrams using shear and moment equations. So maybe some of you may say that you will prefer the first method, but somehow there are times that you need to construct your shear and moment equations in order to solve the problem. So one thing is, what if is this distributed load is triangular or has a 1-degree curve, a 2-degree curve, or 3-degree curve. Okay, let us say that your the shape of your load is like this, or even just triangular load. It will become more difficult. Okay, so let us say this is your 3-degree curve, and this is a 2-degree curve or triangular. So if that is the case, you use shear and moment equations. But in this, but if your distributed load, your distributed load is only uniformly distributed load, rectangular distributed load, and not triangular or in a form of a degree, so you can use the first method, as we see in the second video. Okay, so as I have discussed on the second video. Okay, so this is how you do your shear and moment equations in order to construct your shear and moment diagram. So this is how you solve this one, and this is your the second part. Okay, this is the second part actually, okay, of your shear and moment equations, part 1 and then part 2. Okay, so I hope you understand our lesson. Okay, For this sake, we will have um, another example on the next video. Uh, I will do a part 4 on this series, shear and moment diagrams.